So hi everyone, thanks for coming to Crypto Seminar. Today we have Saeed as our speaker. He is currently a postdoc at Princeton University, and he's going to talk about his work on InstaHide attack. Let's welcome Saeed.
Thank you very much for the introduction and also for invitation. So the title of the talk is Private Learning Possible with Instance Encoding. This is a joint work with my amazing co-authors. All right, so let's start. So machine learning is a process that is a data-driven process that you want to approximate a function, a concept function, by just looking at some examples drawn from the distribution that are consistent with this concept function. For example, you have a data set that consists of samples from dogs and cats distribution, and you just want to find out, learn this distinguish a function between dogs and cats by just seeing some examples from distribution. So one important question in whole machine learning is if we can make this process private. So we need to define privacy, but in general, this intuitively is a very important problem because these data is usually consist of sensitive information that we want to keep them private, and we don't want this process to leak those information. So what we mean by privacy, so there are two kinds of privacy that currently is being studied in the private machine learning literature. One of them, so these are the name that we call them, it might have better names, but we call the first type physical privacy, which deals with the leakage from communication between data owners and the learner. So there are some, imagine there are some data holders that want to share their data to learn a model. So we want this communication between the data owners and the model builder to be private. So these kind of privacy is usually achieved by cryptographic solutions such as multi-party computation or fully homomorphic encryption. But there are also some other solutions based on differential privacy that achieve lower privacy standards, but still are sufficient in some applications. Another type of privacy that is very important is functional, which is something we call functional privacy that deals with the privacy of the final trained model. So this process that you do the training, the first type doesn't care about the output of that model. So it just wants to make the communication private. But here we just want to make sure that whatever we learn at the end does not leak too much information about the training set that is used to train the model. So the mainstream solution here is differential privacy. It has its own drawbacks. It sometimes drops the utility too much. Sometimes it provides not sufficient privacy compared to cryptography solutions, at least. So there are weaknesses on all these solutions, either from utility drop or computational inefficiency. So there is still a lot to be done in the area of private machine learning. So based on these two definitions, there is a new kind of technology that is being promoted for achieving privacy in very recently. So this is the private learning through instance encoding, where the process is similar to the learning pipeline, but we have an encoding layer in between the generating the data set and do the learning. So it's the same thing, but instead of just learning on the plain data, we first encode our plain data to get some sort of encoding and then learn from it and hope that this encoding does not hurt the learning performance, so we still get sufficient accuracy and also efficiency for the learning algorithm. But at least we also want some privacy. So the privacy notions that we can hope for here are both types of privacy. So this is a very appealing notion because it has the potential of giving us both types of privacy. It can give us the private communication or physical privacy that we discussed, because the encoding function could be used as some sort of encryption for the communication between parties and the learner. And also it could give us private learning or the functional privacy, because what we learn at the end is something that is learned from the encoded data. And as long as this intermediate layer encoding is private, using some post-processing argument, we can always argue that whatever you learn from it cannot leak more information than the encoder. And because the encoder is sufficiently private, we don't have to worry about the privacy of the final model. So this is the problem that we want to understand here, and we want to see if it is possible to use this instance encoding to achieve high levels of privacy or not. So is this clear so far?
Yep, it's clear. Thank you.
Okay, great. So what is our motivation to study this problem now? So there was this recent proposal in ICML 2020 called InstaHide that uses the same ideas of instance encoding to achieve privacy. So the accuracy and efficiency that they achieve are surprisingly well compared to the other technologies like differential privacy and cryptographic solution. So if they're actually private, it will be a great improvement over the state of privacy preserving machine learning solutions. So that's why they actually won a Bell Labs Prize for their paper. But what we want to show, what we show in this paper is that the protocol is not that secure. We have some strong privacy attacks, reconstruction attacks against their defense. And we also analyzed the whole technique of instance encoding to see if it is possible to achieve these standard security guarantees from it or not. So basically, the main question that we have is to see if InstaHide or anything similar to InstaHide could be private. But before getting into that, let me give you some just overview of how this InstaHide algorithm works, because it's quite simple and it could be really interesting to see how it works. So InstaHide is an algorithm that uses this dataset, image dataset, to do image classification. So the way it works is that, so we start with a public private dataset that we want to learn. So it's labeled and we want to use it to learn the underlying concept, which is image detection or image classification. So we also have the access to some public dataset that is unlabeled, like images from web. So any image from web could be used here. We don't need any labels here. So we have these two sources, and we want to now encode the private part of the data so that we can learn, we can still learn from. So how does this process work? So we just first sample a bunch of private images and a number of public images, in this case, 2 private and 2 public images, and combine them in a linear way with some random weights. So when we do that, at the end, we get something that is combination of all of them, a little bit not clear what it is, but hopefully the learner can still learn something from it. But we even do more. We also do a random sign flipping operation. So we flip the sign of each pixel with probability half. And at the end, what we get is even more noisy. And it seems that the humans don't get anything out of this noisy image. But surprisingly, if you just do this process with all the images, you get a data set that if you apply the learner on top of it, you still can learn a good classifier that can classify your images surprisingly well. So this is very amazing in how machine learning can actually get any sense of this noisy looking images, but it can. So there's no doubt that the accuracy of this scheme is high, but the question is if it actually provides any privacy or not. The fact that the images don't look like anything to humans probably is not a good measure of privacy. So we want to see if we can get strong privacy guarantees out of such techniques or not. All right, so this was InstaHide, and so the motivation of paper again is to understand this privacy of the InstaHide itself, and also understand if anything that does similar stuff to InstaHide provide any a strong privacy notion or not. So for analyzing InstaHide, unfortunately, the InstaHide paper is not providing any formal refutable definition of privacy that we can break, but they actually have a challenge dataset which enables us to attack it in a concrete way. So we actually break this challenge dataset, which is basically just a bunch of encoded images that they ask us to come up with the images that we use to encode them. So we break that, and we also give some impossibility results for algorithms that use encoding style arguments in their privacy. So we will go through these two in opposite order. At first, I'll give you some impossibility results that we have, and then I'll give you some short explanation of how our attack works. But is everything clear so far?
Sorry, I was spacing out a little bit. So how is this noisy image generated again? By taking the average of the original images?
Yeah, so not all images, but a number of them. So at each, so for each encoded image, you sample some private images and some public images. Let's say 2 public images and 2 private images every time, and you give some random weight to them according to Gaussian weighting, anything. So you can imagine the uniform sample, the weights, and then you just combine them. You get this noisy combination, which is just a combination, but you want to add some noise to it too. The noise that you add is just pixel, you flip the sign of the pixels at random. So with probability half, you flip the sign of each pixel. And these numbers, these pixels are, imagine they're normalized between -1 and 1. So they are centered around 0, and when you flip the flip the signs, it will be something like this. So this is how it generated.
There's a question on the chat as well. How does the private image look like? Is it encrypted somehow?
No, the private images are not. They're just in plain, but we want to encrypt them. So this is kind of an encryption that we use. So this is supposed to encrypt the image by doing this process. So there is no encryption going on here. The only kind, like we call it encoding, but the paper itself calls encryption. So they just combine these images so that they don't look like the original image, and they call it encryption. We don't have any prior encryption before the system.
Is there like some strategy as to like which images are picked to like be composed together?
Just random. No, there is no strategy. Yeah, just picking at random. I guess there's another question. Okay, great. So let's move on. All right. So now, in order to show our impossibility results, we need to come up with formal definitions first, what we mean by privacy, what we mean by encoding, and what we mean by accuracy, because we want to achieve all of them together. So for encoding, there are 2 settings that we can imagine. One of them is more general. We call it dataset encoding, where the encoding algorithm is applied on the global dataset level, and it gives us some encoding of the whole data set. So this is very general, but there is the concept of instance encoding as well, where you can actually encode instances one by one, and just get the encoding of data set by this local encoding of the instances. So these are 2 different types of encoding. The first one is definitely more general, but we have impossibility results for both of them. Note that in the second type of encoding, we can also give the dataset S to the encoder algorithm for instances. So they're not that much different from each other. We can just define this notion of an instance encoding in the second type, but it could be that we, in the dataset encoding, we don't have any sort of notion of instance encoding, and the dataset is just mapped to some weird object that is used for the learner. So these 2 types of encodings we work with. We also work with 2 different notions of accuracy. So the accuracy in machine learning is usually measured using a test set. So you have a training set and test set, both of them samples from the same distribution. You learn from the training set. Here you learn from the encoded version of the training set to get a classifier H. And now you want to measure the success of, or the accuracy of this classifier. So you use test set in that for that. So the accuracy on the original data is defined by the process of just getting instances from tested and see if the label is equal to the correct prediction or not. That will give you the accuracy. But you can also define accuracy on encoded data in this case. And especially for the case of instance encoding, you can first encode your instances and then check whether the label, and then run the classifier on the encoding and check whether the label is equal to the correct label or not. So this is only defined for instance encoding. And this has applications in the case that you want to also do private inference. Like when you want to submit an instance and get the label back, you don't want to leak information. You just can submit the encoded instance and get back the label for that. So this type of accuracy has applications. Interestingly, the InstaHide achieves both type of accuracies, and they have accuracy in both settings. So results that we're going to mention both apply to InstaHide in that regard. So yeah, so these two types of accuracy we define. We also have to define privacy. So for privacy, we have some considerations. So we will define two types of privacy for these two types of encodings that I mentioned: instance encoding and dataset encoding. And we are inspired by the way that InstaHide goes for privacy. So they claim privacy only for the features. So they don't claim privacy for the label of instances. And the logic sounds actually interesting, because you might be okay with leaking the label information of your training data. That might not be something that you care about, at least in some scenarios. And we also want to have notions of privacy that have this property, that the label information is not something important, and we are okay with having that as a leakage in a formal way. As an example of why this is a good privacy notion and what's a good property for the definition of privacy, you can look at this, for example, encoding instances in the bottom of this slide. So if the encoding maps a dog photo to some sort of canonical dog photo, and similarly for cat, it just is leaking the label information, and it doesn't contain any other information about the original image. So this is a fine encoding for many scenarios because it's just leaking the label. So this is kind of an example of why it could be enough for the privacy to just preserve the privacy of the features and not the label. So yeah, so we are the privacy notions. This is an important consideration. So let's see how we define privacy here. So we have two types of privacy again for both the encoding types. Both of them are indistinguishability-based privacy definitions, inspired by the way cryptographic protocols or security of cryptography definitions work. So we want the encoding of instances not to be distinguishable from each other as long as some properties are satisfied. So how does this work? So we have this protocol, we define it based on a security game. We have this protocol consisting of learning algorithm and the encoder. And we have the concept function that is fixed in the security. So this is a parameter of the security game. So we fix the concept function, and now the adversary has to pick two instances so that they are labeling, so they labeled the same according to this concept. For example, it should be either two dogs or two cats in the case that the concept is separating cats versus dogs. The adversary is also selecting a distribution for sampling the rest of the data to do the encoding. So what the challenger does is to just sample the data set from this distribution and then do the encoding for both of the sample, or for one of them at random, and send that to the adversary. And now the adversary should decide which one was encoded. So this is important in this game, that we are forcing the adversary to have the same labels for the challenge images or challenge instances, because as I said, this is something that we are aiming for, to have a privacy notions that doesn't care about the leakage of the label. And we don't want the attacker to achieve the distinguishability through the leakage of the label. So that's why we force the attacker to always submit two images with the same label. So this is the first type of the privacy that we define. But is this clear? If it's clear, I'm gonna move on to the second type. All right, great. So the second game that we define is for dataset encoding. So this is very similar to the way the differential privacy is defined, but with the difference that we are working in distinguishability regime, and we also force the attacker to use data sets that are consistent with the concept function, and also the differing instances are labeled the same way according to the concept function. So what does that mean? So the adversary should pick two data sets that are neighboring, meaning that they only differ in one instance. The labels should be actually consistent with the concept C for all the instances in the data set. And also the label for this differing input, which is the first input in this case, should be the same. Now the challenger, what the challenger does is select one of them at random, encode it and send it to adversary. And now the adversary wants to guess which of these data sets were encoded. So again, here we are also trying to formally be okay with leaking the label information by forcing the adversary to be consistent in the differing input, so that the label statistics doesn't matter here. Is not an important leakage, and we just formally leak it so that the distinguisher cannot use it as a tool to distinguish between these two cases. So yeah, this is the other security game, but we have results for both of these settings that I'm going to mention. But if this is clear so far, I'm going to give you some examples of what this means to be private in these security games.
Can you explain the relationship of the two definitions? And by the way, what's the first definition again? I already forgot about it.
The first definition is for instance encoding. So the difference here is that the adversary selects the two instances, x0 and x1, submit them, and the encoding type that is being used here is an instance encoding. It's not a dataset encoding, and also the rest of the points in the dataset is selected by the challenger from distribution. It's not selected by the adversary.
I'm sorry, could you also remind me what is the concept function? I forgot that.
The concept function is what we're trying to learn. So concept function, for example, here is cat versus dog.
Oh, okay. Okay, thank you.
So it determines the ground truth of the images. All right. So if clear, I'm going to give you an example of what's the difference here. So let's see an example of instance versus data encoding that satisfies the accuracy and privacy notion that we had. So for instance encoding, you can imagine this encoding that just for the case of cat versus dog, that maps cat images to canonical cat images and dog images to canonical dog images. And the learner is applied on this encoded version of a data set that is just nothing just perfectly fine, because it doesn't leak anything beyond the fact that we have a certain number of dogs and a certain number of cats, which is fine based on our instance encoding security game. So this is also, in terms of accuracy, you can see that this can provide accuracy on encoded data, because the learner will be actually can have high accuracy on these canonical images, and hopefully it can also have accuracy on the unencoded images as well. As another example, you can imagine a dataset encoding procedure where the encoding is actually doing something very weird, but it satisfies the definition. So the encoder just outputs, let's imagine the encoder just goes through data, magically finds the concept, the description of the concept function, and outputs the circuit that describes this concept function as the encoding. So the encoding of everything will be the same. It's just the concept function, and the learner will output one of them at random. So this is a perfect learner in the sense that it achieves 100% accuracy on original data, and it is private according to our this dataset distinguishing security game, because if two datasets are the same if they're labeled the same way according to the same concept function, then this encoder will find the concept function and output that. So there is nothing that the adversary can use to distinguish these two data sets. So this is another example of dataset encoding. So it's important that to know that these examples exist, and we cannot hope for proving something that can rule these kind of examples out. But we will leverage the fact that these encoders and learners should be something that work for multiple class of functions and not just one function. So so that we prove our impossibility. So we rely on the fact that the encoder and learner should work for at least two different concept functions, and these solutions cannot work in that scenario. We'll see why. But yeah, so this was just an example to give you a sense of what is the difference of these settings that I mentioned. And we will have two different theorems for both of them. So are the definitions clear so far? All right. So okay, so the main question that we have and we want to answer in our theorems is that can we achieve privacy and accuracy together based on the definition that we discussed using some instance or dataset encoding mechanism? So we have two barriers. The first barrier is for the case of instance encoding. So what we show is the following. We show that if a learning protocol that uses instance encoding achieves high accuracy on encoded data for at least two concept functions. So it's important. The setting that we're working with is instance encoding. The accuracy that we have is on encoded data, and it's working for at least two concept functions. So again, the concept function here is what we try to learn. Let's say we have a concept function of cat versus dog, and another concept function that we try to learn is, I don't know, white pets versus black pets. So if these two cases work, then there is a polynomial time adversary that can break the indistinguishability privacy game for both C1 and C2 with high advantage that is proportional to the accuracy of this learner. So this is the theorem. So I'm gonna give you some insight about how we prove it, and also give you a better understanding of what the theorem is saying. So let's say again, there are two concepts that I said that the learner works for: cat versus dog, black pet versus white pet. So these are the two that the learner can learn it with high accuracy. We want to see how the adversary can use this fact and break the indistinguishability security game. So what was the security game? What is the goal of adversary here? Let's say the goal is to break the game for the first concept C1. So the rule of the game was the adversary has to provide two images that are labeled the same according to the concept. So it either should provide two cats or provide two dogs. So let's see how the adversary does that. The first step the adversary makes is just to train a classifier on the second concept in its mind using the protocol. So the adversary can sample data from distribution, can label them, and train a classifier. And we know that this classifier is good on encoded data because we know that the protocol gives us high accuracy on the encoded data. Now that we have this classifier, we want to use it to break the security game. How do we do that? So the adversary selects two cat photos that are, one of them is white, one of them is black. So this is the challenge photos. And this is, so far we are complying by the game because the game required us to send two images that are labeled the same way. These are both cats, so we're fine. And we are trying to break security game for C1, and there's nothing that we're breaking so far. So the third step is to just receive the encoding of one of them. And now the adversary has to decide which one was encoded using the classifier H2 that it trained in the first stage. So what the adversary does is basically feeding this encoded image to the classifier H2. If the label was black, it means that the black photo is encoded, and if it's white, it means that the white cat was encoded. So it all boils down to the accuracy of this classifier H2 on the encoded data. And because we have that as a guarantee in our theorem, it means that we can break the security game with advantage proportional to this accuracy of H2. So is this clear?
Yep.
Nice. So, all right. So this is the simpler version of the theorem, but you can actually extend this. So here we just assume that the attack works on two concept functions, but it could actually work on many other concept functions too. And it's usually with learning algorithms. You don't accept the learning algorithm just work for one function. You expect it to work for anything that you throw at it, as long as it doesn't have a lot of complexity in it. So if we can actually extend the number of concepts to more properties, you can train more and more number of classifiers, and this helps you to come up with a profile for each encoding. So at the end, this makes the attack much stronger in the sense that, first of all, the attack doesn't need to find the two challenge photos. The challenge photos could be just sampled from the same distribution that is used for training. And that will be still a successful attack, because the attacker can just look at the whole profile, and the probability of the profiles looking exactly the same is too low, or even being close to each other is too low, and it gives the attacker the power to distinguish, even though the attacker did not choose the challenge images in the worst case, and they just sampled it from distribution. And it can also help the attacker in another way, which we didn't explore here, but it is that it can actually get more and more information that can help it to reconstruct the image. So as if we are doing this and we are getting more and more properties of this original image, so we might be able to feed that to another like crazy neural network that can reconstruct the whole image based on the properties that we give it. So this is not how we break InstaHide, but this could be a possibility, at least for some scenarios, that getting more and more information can lead to better reconstruction. So basically, we are reducing the entropy of the original image by getting each property, and hopefully we can reconstruct it after several queries. So this is basically the extended theorem that we have that I didn't mention formally, but you can use this idea to make the attack stronger. And I'll get back to this when I'm also describing the attack on InstaHide, or how these similar ideas could be helpful to break this InstaHide itself. All right, so this was our first theorem and first barrier. We also have another impossibility result for the case of dataset encoding. So as I said, dataset encoding is much more general, and we cannot have the accuracy on the encoded data anymore, because it's even meaningless to define it. So the accuracy is only defined on the original data. And you still want to prove some impossibility result. We cannot use the previous techniques because that heavily relied on the fact that the accuracy is high on the encoded data. So let's see how we prove this and what's the theorem actually saying. So we again assume that the learning algorithm and the encoder work for two distinct concept functions on a fixed distribution. What we prove is that there is a polynomial time adversary that can break this the indistinguishable security game for dataset encoding with advantage half plus 1/6, and where n is the sample complexity that you need to learn a non-trivial classifier. And this works for either of C1 or C2. So we don't prove it for both of them anymore, but for just one of them. So here the bound is weaker because we are relying on the sample. So it depends on the sample complexity in an inverse way. So the bound is weaker than the previous theorem, but this is expected because there are subsampling solutions that make this theorem actually tight, kind of tight so instead of 1/6, and you probably can have 1 over some constant times 1/n. But in terms of in asymptotic way, it's tight. So I'm not gonna talk about that kind of subsampling technique because it's not that interesting. But I just want to mention that this is something that we have to expect for the advantage of the attack to go down by when we have more and more samples. All right, so let's give a proof sketch for this theorem if it's clear. So as I said, we cannot use the previous techniques. We have to use new techniques. So what's the goal of attack here? If you remember the security game of this encoding, the attacker should submit two data sets that are neighboring and are consistent according to the concept function. So we start with the two data sets that don't have any of these properties. So this data set S1 and S2. So the first data set is a bunch of cats labeled 1 and a bunch of dogs labeled 0. And S2 is the opposite. Cats are labeled as 0, dogs are labeled as 1. So as I said, these two data sets are not neighboring and are not consistent with any concept function. They're exactly the opposite. But the important property of these two data sets is that if you encode them, the adversary can actually try to use the learning algorithm on top of encoding to learn a classifier and check if it's closer to the original concept of cat, the concept of S1 or the concept of S2. This is easy to check because you can just sample inputs from distribution and see if it's agreeing more with C1 or 1 minus C1. So this is easy to distinguish the encoding of these two cases for the adversary. But the issue is that this is not an attack yet because we are not complying with the security game. The security game required us to be consistent according to the concept function and also being neighboring. So the neighboring issue can be resolved, but let's ignore it for now and just focus on making these two data sets to be consistent with the fixed concept function. So how we go with that? So we define two other data sets, S3 and S4. So these data sets are again cat and dog photos, but some of them are white, some of them are black, and the labeling are dependent on the white and black too. So we have a bunch of white cats labeled according to 1, a bunch of black dogs labeled according to 0, labeled 0, and the S4 is actually the opposite. There are white dogs labeled 1, black cats are labeled 0. So now I want to show that 3 pairs of data sets that all of them are consistent with a fixed concept function, and the attacker should be able to distinguish at least one of them with high accuracy. So the reason is, so first of all, if you look at S1 and S3, they both consistent in the sense that cats are labeled with 1, dogs are labeled with 0. S3 and S4 are consistent in the sense that white pets are labeled 1, black pets are labeled 0. And S4 and S2 are consistent in the sense that dogs, again, are labeled 1, cats are labeled 0. So although the start and the end are not consistent with each other, we can get to, we start from the first data set and get to the last data set by a number of pairs of consistent data sets. So what, with a hybrid argument of, with 3 hybrid arguments, we can basically show that there at least should be one of these pairs that the adversary can distinguish them with high probability. And because we have that now we want to resolve this second issue that we had, which was that the data sets are not neighboring. So again, we will have an n-fold hybrid argument starting from the data set, changing instances one by one. And at some point, based on the hybrid argument, you have to have a distinguishing probability half plus 1/6 times n. So this is basically the sketch of the proof, and I hope it wasn't too dense in this slide. But this is just this simple idea that you can just start with the attack on the data set of S1 and S2 and extend it to 2 data sets that are neighboring and consistent with the fixed concept function. Was this clear? Is this is there any questions on this slide? All right, so now that we're done with the proof, the impossibility results, now let's get to our actual attack here on the InstaHide protocol and see how it works. So the attack algorithm has two parts. The first part is to do a clustering, and the second part we use this clustering to do the recovery. So what does the clustering do? So InstaHide encodes different images multiple times with fresh randomness every time. So you expect in the challenge dataset to see multiple encodings of the same image, and if you can actually cluster these multiple encodings together so that you have a bunch of encodings of a single image, then we show that we can use this clustering to do the recovery very easily. Actually, doing the recovery after the clustering is not that hard because even it's simple averaging over the clusters, actually taking the absolute value and then doing the averaging will give us some kind of accurate images. But it's not what we do. We actually solve a system of linear equations with noise to come up with the images after doing the clustering. But yeah, that's simple too. So the hard part of the attack is to do this clustering stuff. And I'm gonna explain a little bit how we do this clustering here. And the recovery is just, as I said, solving the linear equation with noise. So the clustering task, as I said, we want to match different encodings together based on the image that they're encoding. So one possible approach to do it, based on what we discussed so far, is to use the profiling technique that I mentioned in the first theorem to come up with a profile for each encoded image. So we know that the encodings here are the encodings here are going to preserve the accuracy, and we can run the classifiers on top of them. So if we have a bunch of concept functions that can uniquely determine the images, we can use those concept functions and train classifiers based on them to get the profile for each image and match the images based on that profile. And that will give us a clustering like this. So the clustering step could be done this way, but this is not how we did it, because it takes some time to find the concept functions and train a different classifier for them. We just leave it to a neural network. So what we do is we train a neural network that actually automates all the process for us. It has to find out if two images are two encodings are sharing an image in their encoding process. So the way we do it, we generate a bunch of encodings on our own. So we can use a public data set to do that. So we generate E1 to En, our own encodings, and we know which of them are sharing an image in their input or which of them are not. So which of them encoding the same number value or they're not encoding the same thing. So that's something that we know, and we can pair them together and label that based on that information. So we have a data set now of pairs of images and that are labeled according, pairs of encodings of images that are labeled according to whether they're encoding the same image or not. So we can train a model on top of this data set and hope to get a similarity measure that works, generalizes to other data sets and other distributions as well. And that's actually the case. So when we train this classifier, we get very high accuracies on scene data, around 90% accuracy. And that helps us to do the clustering. And as I said, after the clustering, it's simple solving the linear system of equation. So that's basically the attack. So this part of the attack has some other subtleties as well, but the main part is this, constructing the similarity metric that gives us whether two images are sharing an image, two encoded values are sharing the same image or not. So yeah, after this, the attack is done and we get these reconstructions, which are pretty similar to the original images that are used for the dataset. So this is actually the challenge dataset that InstaHide paper provides. And as you see, it's basically extracting everything from the image. And yeah, so that's it. So the paper, we showed that InstaHide is not secure against the reconstruction attacks that we have, and we also show impossibility results for achieving the strong indistinguishability privacy against these instance encoding mechanisms while they preserve accuracy. So the results that we had are all rely on the fact that the protocol should work for at least 2 distinct concept functions. But a question that one might ask is, what if these encodings are ad hoc to a specific problem? So we cannot, our theorem do not work in those scenarios, although we have another theorem that I didn't mention here that says even if it only works for a single concept and it's just ad hoc to a single task, it means that the encoding should be as good as the classifier, meaning that it has to contain every information that the classifier does, and we can basically learn the classifier by just having access to the encoder, and you don't need anything else. So yeah, so these kind of impossibilities also shows that any algorithm that uses similar techniques cannot be having as strong as the cryptographic privacy that solutions like fully homomorphic encryption or multiple computation provide. All right, so that was it. Thank you very much, and let me know if you have any questions.
Can you maybe like generalize the attacks that you guys did, like not only for InstaHide, but like other approaches that are similar?
You mean generalizing for instance encoding mechanisms?
Yeah, like, yeah, instance encoding and like all of the like similar works, I guess.
So one important thing in our reconstruction attack was that the instances are encoded multiple times, and that was a crucial part of getting this reconstruction. So if a mechanism doesn't do that and just encode everything just once, I think this reconstruction might not work anymore, but our theorems still stand. So I don't think we can generalize this to any instance encoding mechanism unless there is some sort of multiple encoding going on. But that's a good question. If we can prove some sort of impossibility results against reconstruction attack for reconstruction attacks, showing that you can actually reconstruct given these instance encoding mechanisms that are preserving accuracy, but we didn't prove that. So yeah, to answer your question, I don't think we can generalize this to a general case of instance encoding.
Okay, thank you. Makes sense.
So if there's no question anymore, let's thank Saeed again. And I guess that's it for today.
Great, thank you very much. And thank you again for inviting me.
Thank you, Saeed.
Yep, thanks.
Thank you for the talk.
Yeah, thanks.
Yeah.
Thanks.
Thanks.
Bye.
Bye.